In the previous lecture, we had the model theory for propositional logic. That is, we saw the syntax and or not, etc., and the semantics with truth tables. And we saw some simple manipulations using normal forms. But now we need to look at how to prove theorems in propositional logic. What I'm showing you here is a simple proof calculus for propositional logic. So K is the name of an axiom, S is the name of another axiom. These are axiom schemes, that is to say, where you see A, B, C, these can be replaced systematically by any propositional formula. So, if you like, axiom K abbreviates infinitely many different axioms, but all having the form shown. Now, axioms K and S will look pretty weird to you, but at least axiom Dn, which stands for double negation, should be pretty obvious in what it's telling us. That is to say, not A implies A, and we have a copy of that for every formula A. In addition to these three axiom schemes, we have one rule of inference, which takes as premises something of the form A implies B, something of the form A, obviously we mean the same A, and delivers as its conclusion B. This at least should be obvious to everybody. So those three axiom schemes and that one inference rule are our proof system. Now you might say, what about other connectives that we might be interested in? Things like or and and. Nothing about them is said here, and so they have to be regarded as abbreviations, so one can rather awkwardly define, for example, A or B in terms of, I guess, not A implies B, and so on. Well, to see how this works, let's prove something. So, let's prove A implies A. We're here, by A, I mean, again, it's a schematic proof, if you like, because A here is an arbitrary formula. It doesn't matter exactly what A is because the proof is the same for every formula A. So in the first line, you see the lines are numbered from 1 to 5. The first line is an instance of axiom S. It may not seem very obvious to you, but if you go back to axiom S and see you plug in this thing, this D implies A, into axiom S, and I guess we have to plug in A implies A as well. Yes, it's not so easy to see, but after a little while we convince ourselves that this is indeed an instance of axiom S. The second line is an instance of axiom K. Here we have simply plugged in the formula D implies A in place of the formula that was called B in axiom K. Now looking carefully, we see that modus ponens is applicable to the previous two lines, giving us the conclusion of the first line. We then find another instance of axiom K, and using that instance with line 3, we come up with A implies A. Now in the past, I recall despairing students asking me why you can't just say, I have A, therefore I know A, or something. And this is a bit like asking why in a football match you can't just pick up the damn football and run with it instead of having to kick it everywhere. The reason is it is against the rules. The rules that we have here were given on the previous slide, and they are all we have to work with. Now, it turns out that this proof system is complete for propositional logic. That is, it can prove everything that's a theorem. but it turns out the lengths of proofs grow exponentially, even for trivial looking things like this. I'd like to make a further aside concerned with propositions as types. It's not really part of the course, but it's interesting. So this particular axiom system is not random. Now, if you look at a bunch of logic textbooks, you will see a variety of axiom systems for propositional logic, and some of them do look pretty random, at least to my eyes, but not the ones I have shown you here on the first slide. So first, let me recall, perhaps you may remember from the semantics course, an inference rule for applying a function to an argument. So I have a function f of type A arrow B, an argument little a of type A, and the result, that is the result of f applied to A, having type B. Strip away the terms and you get something that looks like modus ponens, assuming we're willing to identify the implication A implies B with the function type from A to B. In a similar vein, the axioms S and K turn out to correspond to some obscure things connected with the lambda calculus. They are called combinators, and the types of these combinators are as shown on the first slide. So in fact, we get through this axiom system a correspondence between the theorems proved using the axioms and certain terms of the lambda calculus. Now, once you have a proof system like this, it's normal in logic to look at the so-called meta-theory. That is, to formally analyze what can the formal properties of this system. The most important thing we want to know is that if our proof system asserts that something is a theorem, then it really is a theorem. And almost as important as that is the converse property, that if something is a valid formula, then it has a proof in our system. So looking at these, the first property is called soundness, and to put it more precisely, if A is provable from S, so that means, or is deducible from S, that means we can create a proof using our proof system, using as additional axioms elements of S and culminating with A. If that such a proof exists, then S entails A. So here we are linking the proof system with the semantics of propositional logic. This is the most important property because clearly, what is the use of a proof system that tells you that things are theorems when they don't actually follow with the truth tables? Almost as important is completeness. So if S entails A, here S having to be a finite set because we have only finite proofs, if S entails A, then we would like there to exist an actual proof of A from S. It's not possible in every logical system to have completeness, but in the case of propositional logic, there exist complete proof systems, and so we would want to insist on this property. There are other properties that could be proved, in particular of this proof system. So here we have the deduction theorem, which says, suppose I have a proof of a formula B, and I can regard this proof as being based on assumptions in a set S, of which I distinguish one in particular, some A. So A, together with other assumptions S together, allow us to prove B. Then it turns out that S proves the formula A implies B. At first sight, one might think this should be obvious because in some intuitive sense the meaning is the same. But it's not obvious. It's obviously desirable. It's obviously natural. But one can come up with proof systems for which this particular property doesn't hold. If you have a well-designed proof system, you can prove lots of meta-theory like this, and yet, as we saw in the previous slide, in the proof of A implies A, that the proof system might be completely impossible to use in practice. And this reminds me of a little joke I heard when I was a student at Caltech. It wasn't an amazing joke, but it was something about distinguishing between different kinds of physicists, engineers, and so on as to how they would put out a fire in their bed. So, as I recall, if the engineer discovers his bed's on fire, he looks and he finds a jug of water on the bedside table. He tips it all out and he puts out the fire thoroughly. Okay. And what about the mathematician? Well, the mathematician wakes up, sees that his bed is on fire, notices the jug of water. He says, "Ah, there exists a solution," and goes back to sleep. So you see, mathematicians like to talk about doing a thing, but they never actually do it. This may explain why they almost never have any children. So we are different. We would like to do the thing, that is to say, we would like to prove actual theorems using our proof calculus. For this, we need an entirely different kind of proof calculus from the one we have seen so far. The previous sort tends to be called Hilbert systems. The distinguishing feature of Hilbert systems is they are based primarily on axioms with one or two inference rules, and you're working strictly with formulas. Gerhard Gentzen introduced what he called natural deduction with a richer proof context in which you have assumptions, a set of assumptions that can actually vary as you work through your proof. This comes out in a very simple and natural manner. Let's say you're trying to prove A implies B. You assume A and then you prove B. So if you want to say, I don't know, all even primes are equal to 2, then you assume that X is even and prime. You make that an assumption, and then you do a little work and you discover that n is equal to 2, and you're finished. And once you're finished, you are no longer assuming that n is equal to 2. You've just got your theorem. Another distinguishing feature of natural deduction is that the various logical connectives are defined independently from one another. So as whereas on the first slide we saw various rules involving the implies symbol and negation, and with other proof systems one might see, typically you see a lot of implies jumbled up with the ors and ands in any kind of way. With the Gentzen system, there are many types of Gentzen system, but one thing he emphasized was that each logical connective is defined independently of the others. So right here you will see we have rules for conjunction, that is A and B. So the first rule here says if I have A and if I have B, then I have A and B. That's called an introduction rule because it introduces the connective, namely conjunction, in its conclusion. There are also two rules that start with A and B. One of them concludes A, the other one concludes B. Rules of this sort are called elimination rules. In this case, you are given something involving your connective, and the rules show you what you can deduce from it. We're not going to talk about natural deduction very much in this course, and the purpose of this slide really is to show you why we're not. So here is a proof, and you don't need to understand this proof. I haven't really equipped you with the rules needed to do this proof. The most important thing to see is there are things crossed out in the proof, because the way one works with natural deduction is you assume things, you use them, and after you've used them, you cross them out at a particular point in time. You're meant to cross them out in the right order. And if you are thinking of myself trying to mark your exam question, I have no idea whether you've crossed out these formulas in the correct order or not, because what I see at the end is simply that they have been crossed out. It is a relatively natural way to work, but the crossing out can get a little confusing and messy. There are some advantages to natural deduction. So here I'm presenting a few more of the rules just for you to see what they look like. So here are some introduction rules for disjunction, followed by the modus ponens rule, which we have seen already. It's also part of natural deduction. There is a further drawback of natural deduction, namely that for the classical logic, which is the focus of this course and the focus of almost all automatic theorem proving, doesn't actually go so well in natural deduction. You really have to struggle to prove some fairly obvious things. So we are going to say goodbye to this particular sort of proof system. We are still staying with Gentzen, however, because he also invented the sequent calculus. The sequent calculus can be seen as a cousin of natural deduction, in which you never have to cross anything out because you never write anything up at the top of the page to be crossed out anyway. What you do instead is make all the assumptions explicit on every line, simply by writing them out in a list. And when an assumption is no longer needed or is no longer available as an assumption, it simply disappears from the list when you copy out that line. And that way, there is no crossing out, and at every line you know exactly what you're allowed to assume. So we work with things called sequents, which have a bunch of formulas on the left side of a big arrow and a further list of formulas on the right. Now, you might say, oh God, we have another thing that means implication. That's not so. So the sequent arrow is part of the sequent calculus. So you get to have exactly one in every sequent. It is not part of a formula. So it is not a new logical connective. It is simply the way we write a sequent. The meaning of this sequent is simply that if all the things on the left are true, then at least one of the things on the right side is true. So we can see the formulas on the left as assumptions. We can see the formulas on the right side as goals where only one of the goals needs to be solved. Now, to save writing, because I get tired of writing all these triple dot things everywhere, I will often use Greek letters gamma and delta to represent these sets of formulas or lists of formulas. One can be kind of careless about whether they are sets or lists, but I should emphasize their order. The order of these formulas is not significant. Now, the first thing to know about the sequent calculus, and it should be obvious, is that if you have the same formula on the left side and on the right side, then the sequent is trivially true, simply because one of your assumptions is identical to one of your goals. Therefore, no work to do. We can write this using the Greek letters to abbreviate. As you can see at the bottom, a comma gamma, sequent arrow a comma delta, which is a way of saying anything that contains the formula A on the left and also on the right is trivially true, and the name for such a thing is a basic sequent. Now, there are a lot of rules in the sequent calculus. In fact, there will be more on the next slide. Before you despair of the need to memorize, I should point out that there's a lot of duality here. That is, you will see a lot of patterns, and by the time we get to the final lecture in this course, we shall have reduced the number of essentially different rules in the sequent calculus to simply 3. So there is really not a lot to memorize here, as it turns out. Now, I suppose I should go through these rules and try and make sense of them. The first rule is very special. It's special in an odd way. It is a rule you will never use in a typical exercise or exam question, because theorem proving methods never use it, but I may as well try and explain it anyway. The story of this rule is as follows. Suppose I'm trying to prove some sequent, which is written simply as gamma arrow delta, any arbitrary sequent here. It is sufficient if I can prove some formula A, any formula I please, and then if I can use that formula A to continue a proof. In other words, you can regard A as a lemma. So as a simple case, you might regard A as a lemma being proved with the help of gamma. And now we use A along with gamma to prove delta. Then it follows that from gamma we obtain delta. Now, why is this useful? And it might be obvious to you that this must be true, because if A follows from gamma, then adding gamma to A doesn't really tell us anything. The idea is simply that A might be a lemma, or if you're a computer scientist, you could think of it as a subroutine. By proving this lemma A once and for all, it may have a very long proof, but having proved it, then if we add it to our assumptions in the second premise, we can now appeal to this fact over and over again without repeating the work of proving it. In fact, the bit of meta-theory for which Gentzen is most famous is that any sequent calculus proof involving this rule, this cut rule, can be replaced by a proof that does not use it, the so-called cut elimination theorem, which who knows, some of you may even have heard of. Well, that was a long explanation, but you probably won't need to use this rule ever. Now let's look at some of the others. You'll see that they have these little labels. For example, negation L, that means not on the left. Negation R, that is negation or not on the right. Then further down we have conjunction on the left and conjunction on the right. So these are the analogues of the introduction and elimination rules of natural deduction. So, in fact, if we look first at the bottom right, at the rule for and on the right, you might see this actually looks very similar to the natural deduction rule for conjunction that we saw earlier. That is, this conjunction rule seems basically to be saying that if I can prove A and if I can prove B, then I can prove A and B. The gammas and the deltas are just expressing, they are placeholders for the rest of the context, if any. That is, they are placeholders for any other formulas that might be floating around there. But this rule is essentially the same as the natural deduction one. Now, staying on the bottom row, we have the and on the left rule, which turns out to encapsulate the two natural deduction elimination rules in a single rule. So as you recall, in natural deduction, if I know A and B, then I also can deduce A, or separately, I can deduce B. But what this sequence rule and on the left is telling us is that in order to prove something that has A and B on the left side, it is sufficient to prove a formula in which A and B are separate formulas on the left side. So by applying this rule, we have removed the conjunction symbol. As for the not on the left and not on the right, an immediate thing you see is that they remove the negation symbol and move a formula from one side of the sequent arrow to another. So the one not on the right is probably easier to understand, and it tells us that if we are trying to prove something of the form not A, it suffices to assume that A is true and then continue. Now, in particular, if delta is empty, the empty set of formulas, then that is equivalent to false. And then you see that to prove not A, it is sufficient to assume A and then prove a contradiction. So this, again, I hope sounds like logical reasoning to you. I'm sorry to say that we have more rules. Let's look at or on the right. This is dual to and on the left, so you might see a similarity in the shape of this compared with the and on the left rule that we saw on the previous slide. It shouldn't be hard to understand because, as I've mentioned, the formulas on the right side are goals and you only have to prove one of them. So if I am trying to show A or B, then clearly it's enough to show the sequent A, comma, B, where to prove this sequent, I only need to prove one or the other of them. So that clearly has the effect of or. Moving over to the left now, the or on the left rule maybe reminds you of one of the equivalences I showed you in a previous lecture. So if I'm trying to show something and I know A or B to be true, then we can think intuitively that either A is true or B is true. So we prove it with the possibility that A is true. You cover that case. And then we say, well, yeah, but maybe it's actually B is the one that's true. So we go and we consider the other case of B being true. And if you've covered both the A and the B cases, then you have covered both cases. As for the other rules, the implication on the right maybe will remind you of the natural deduction rule for implication that we've seen already, and it is the quite simple idea that if you are trying to show something of the form A implies B, then you can assume A and show B. The one of implication on the left is probably the weirdest looking one. It tells us that if we know A implies B, and we're trying to prove something, we can go about this by, first of all, proving A to be true, and secondly, continuing our proof now with the knowledge that B is true. Another way to wrap your head around these rules is to imagine expanding A implies B into not A or B, and then you should be able to work out that you get the same effect with the sequent rules, that is, you get the same effect with not A or B as you do with A implies B. I should stress, however, that you can't do this when you're actually doing a proof. That is not allowed. You have to stick to the rules, but it can be useful to help you understand the rules. Now here's a teeny tiny example. So let's suppose you're asked to prove a formula like this trivial one here. The first thing you do is turn the formula into a sequent by putting a sequent arrow in front of it. And of course you better put it to the right of the sequent arrow because it's a thing you're trying to prove. Now the interesting thing about the sequent calculus, and you'll see our approach to proving things is totally different from proving things in the Hilbert system we saw on the first 2 slides of this lecture. Here we have, in fact, no choice as to what to do much of the time. In the sequent calculus, you are only able to affect the outermost symbol. The outermost symbol here is this implies symbol. And the only thing we can do, because it occurs on the right side of the sequent arrow, is we can consider that this arose by applying implies on the right. You see, we will write out our proof backwards. And here I wish I could be in a live lecture hall with you because I would write this thing out. I would first write this formula here. Then I would say the only thing we can touch is this implication symbol. So then I would write and on the right, and then I would copy out this formula here, this sequent I mean, A and B, sequent arrow A, as the first step of our proof, working backwards. And then I would continue. So now we have only one symbol left, namely and. It's on the left side, so and on the left is the only possibility, and we would write out this sequent here, which would arise from and on the left. And so we would see A comma B, sequent arrow A, and now we would note that A and B are the same formula on the left and right side. Therefore, this is a basic sequent, and therefore we would write this final rule, this final line above the sequent, just to emphasize that it has been proved and that this thing is a theorem. So let's pretend I did that in front of you. Now a few remarks here. So as I said, you have to work upwards, you're working backwards. You start with the formula that you're trying to prove and you work backwards, reducing it to simpler and simpler sequence until they're all trivial. You will find yourself inclined to skip steps, to take several similar looking steps and pile them up into a single line. I'm sympathetic to the amount of writing you have to do here, but I must point out that I see an awful lot of mistakes being made. And finally, you have to resist the temptation to combine techniques from different approaches. If you're doing a proof in a particular sequent calculus, then that's what you've got to do, and you can't suddenly do some sort of step that made sense in a different context. Here's another little example, and you might notice it was mentioned in the second lecture, and it is the so-called paradox of material implication. So it's a rather weird looking formula. As I said, A implies B or B implies C. Is that really true? Well, let's try to prove it. And remember, so pretend I'm writing this out in front of you. I would write this thing out first, after the sequent arrow, which is here. Then I would say, there's only one thing we can do, because the disjunction symbol is the only one, it's the only outermost symbol, and therefore it is the only symbol we have any influence over. So the rule that we use must be or on the right. And you see how deterministic this is. It's not completely deterministic, but it is significantly deterministic, which makes it very amenable to machine implementation. So or on the right basically turns this disjunction symbol into a comma. And now we do have some choice. We have two implication symbols here on the right side, and we can elect to do either of them. Now I avoid skipping steps, and I am, in fact, in this case, I have chosen the first implication symbol. It was an arbitrary choice, but you see that now the implies on the right rule has moved the formula A over to the left of the sequent arrow and left us with B on the right. We still have one logical connective remaining, that is implies on the right. And when we apply that rule again, we get this thing, AB, BC. That is a basic sequent, and therefore we're finished. Now, a small non-examinable remark here. In case you really hate this particular paradox and find it unnatural, I should remind you that it turns out this is not provable in constructive logic. Okay. Back to what we're doing. Here's a distributive law. Now what I have done, I have in fact skipped a step by not using implies here. I have started with an actual sequent. So formula on the left, A or B and C, sequent arrow, A or B and A or C. So, in fact, you will find in exercises and exam questions will sometimes give you a sequent to prove rather than a formula. So we begin our proof by writing this at the bottom of a blank sheet of paper, and then we work upwards as usual. Now we have a little choice because we have or on the left and on the right. We could have chosen either. I arbitrarily chose and on the right. And what we've got here, if you look at the right hand side, you say A or B and A or C, and it turns out these have almost identical proofs, which is why I cheated here by writing similar. A little hint if you find yourself doing exam questions, writing the word similar whenever you don't have time to finish your work is not sufficient. But if there really is a similarity, and in fact if I wrote out this other proof, it would indeed have exactly the same form. So in this case I'm being honest and it really is similar. Anyway, back to our proof. We applied and on the right. That means we have the same formula on the left, and we are trying to show A or B. The proof that I omitted would be a proof of A or C from the same assumption. Now we have choice because we have or on the left and or on the right. And I'll give you a little hint. Here I chose or on the right because it allows us to do less work. If I did or on the left, it would give me two premises, and it would therefore I would have to write a little bit more, although the proof would still come out. So I applied or on the left, and you can see the disjunction symbol has turned into a comma. Now the only outermost symbol is this or here on the left. So I am now forced to apply that rule. And now I get two premises here. One where A is true, and of course I get a basic sequent. And the other where B and C is true, where with one final step, that is and on the left, gives me another basic sequent, and we're finished. And just as a remark, yes, as I said, the other subtree is just about the same. To complete the distributive law, we would have to prove the converse, that is, we would have to prove that this thing here implies that thing over there. That's also a very routine proof, a very simple exercise if you'd like to do that. Now, it's interesting to see what happens when your proof isn't valid, when your formula isn't valid. And I hope you'll recognize this formula as the one we saw in the previous lecture. It's not a tautology, and it turns out because we have a complete proof calculus, we can even learn from failed proofs in the sequent calculus. So the first thing we try is implies on the right. That's the only thing we can try because it's the only outermost symbol. So we have A or B on the left, B or C on the right. Now I apply or on the right, turning this disjunction into a comma. So now I have two alternative goals to show. That is, it's enough to show B or it's enough to show C. And now the only symbol left is this or here on the left side. I apply or on the left, and what happens? Well, I get a basic sequent for the case where B is true. But if A is true, I'm being asked to show that B or C is true, and there's no reason why they should be. I can falsify this. It's false in the case where A, now we're dealing with formulas and not propositional letters, but nevertheless, if A is a true formula and B and C are false formulas, then this sequent becomes false. We can indeed check that the same thing happens with the original formula. So here is a different way of determining that this particular formula here, A or B implies B or C, is not a tautology. Now, how does all of this relate to automatic theorem proving? It turns out it relates very powerfully indeed. So there was a paper called Towards Mechanical Mathematics, published by Hao Wang. And although it's a rather long paper, within it you will find all the sequent rules. In fact, first of propositional logic, and then he continues with first-order logic as well. And the proof method that he provides, that he has implemented, that he reports on, is doing exactly what we have been doing by hand. That is, taking a formula, creating a sequent from it, and using the sequent calculus rules backwards. So he did this on an IBM 704 computer, a Valve computer. Google it. There are some amusing pictures of it, gigantic thing. And you can see photographs of its circuit boards with these valves. So very, very primitive machine. Nevertheless, showed it was applied to a very large collection of problems from Whitehead and Russell's book Principia Mathematical, and it proved all of them in, I think, something like 3 minutes. So a truly spectacular result, certainly for 1960. And similar techniques are used today in the so-called tableau calculi. We will see little hints of this later in the course. Funnily enough, for historians of artificial intelligence, they are more impressed by other work that was, shall we say, heuristic, trying to emulate human thought, even though the performance of such systems was infinitely worse than what Wang was able to obtain.